Hello, welcome to this lecture on AVL trees. My name is Nzako Baloyi, and it is my pleasure to take you through the incoming material. What do we hope to achieve with this lecture? I hope to, by the end of the lecture, have established the following with you: to have created an understanding of AVL trees, their basic operations, as well as the different types of rotations one can perform with AVL trees. By way of introduction, AVL basically stands for the initials of the persons that discovered this particular data structure, who are Adelson, Valensky, and Landis. An AVL tree is a binary search tree that is height balanced. And you'll see what we mean by height balanced. But as for binary search trees, I trust by now you are quite familiar with them. An AVL tree is a binary search tree with an additional balance property. This balance property is basically what makes the height balancing. The balancing property says one must not exceed the balance factor of -1 to 1. In other words, the balance factor for a balanced AVL tree must be -1, 0, or 1. And any value outside that range results in an unbalanced tree. Now, the height of the balanced subtree, the left subtree, and the height of the right subtree should differ, in other words, by at most 1. That is what that property says. But this balance factor, how do we calculate it? You basically subtract the height of the left subtree with the height of the right subtree to determine your balance factor. Moving on, there are different types of rotations. There are single rotations and double rotations. With single rotations, these we call zigzag rotations. The double rotations, we call them zigzag rotations. Looking at the table before you, the top left is the left-left rotation, which is a single rotation, also called a zigzag rotation. All that says is that given a left skewed tree, all you need to do is to rotate the middle element with the top element to the effect that 4 in this case becomes the root or the parent. And by doing that, because the balance search tree, 5 will fall to the right of 4 and 3 will remain where it is, effectively giving you what you see right here. It's as simple as that. With the right rotation, which is also a single rotation, you have a right skewed tree. And again, you rotate, but this time to the right, all right? The middle element with the top element or node. By doing that, this will push 1 down to be a child of 3, and 3 will become the root node, and 4 will remain where it is, effectively giving you that. That is pretty simple. So the LL and RR are basically a mirror reflection of the other, one just addressing a left skewed and the other the right skewed tree. Now, things get a bit interesting here when we start to look at the left-right, which is a left-right rotation, which is a double rotation or a zigzag rotation. That is to your bottom left. Now, if you look at how this structure looks, because this is our original tree, it looks almost like an angle bracket. Okay? Now, given this angle bracket looking like 3, we need to do 2 rotations to bring it in line. One is to make sure that this tree, after the first rotation, it becomes like an LL rotation, an LL rotation, and so that we can perform an LL rotation on it to get to where we want to get to. So now, let's look at this. Given this tree, we need to rotate the bottom element with the middle element, effectively making 18 take that position where 11 is sitting. But 11 now will be to the left because it's less than 18. So it will be a left child of 18, which is basically what you see here. But now that you have got a left skewed tree, what you need to do is exactly what we did here at the top. You then need to conduct a left rotation of the middle and the top, meaning that the 20 will fall down to the right of 18 because it's greater than 18, and then the resultant tree will be the tree that you have right here. How simple. Just remember, in an angle, as an angle looking kind of tree, you need to do 2 rotations. Okay? Moving on to the right-left rotation, which is also a double rotation, therefore zigzag. What you need to do here, you'll notice that it's just the opposite of the other. Okay? So it's almost like a greater than. What you do here, you just need to rotate the bottom element with the middle element. The minute you do that, 25 goes there, and 30 goes to the right of 25 because it's bigger than 25, and you'll remain with this arrangement here. The minute you have that, you can then perform exactly what you did at the top here, which is to say, you perform a right rotation of the middle element and the top element, which here is 25 and 20. So 20 will come down here, and the tree will be complete. So 20 becomes, just goes down there, and then that is your resultant tree. Pretty simple, right? I trust that you will, if you struggle with this, replay this part of the video until you get the principles, because this is very important. Okay, there are some basic operations that one needs to take into consideration with AVL trees, and these are not exhaustive, but those that I thought are important to raise. One of those is insert. With insertions, these are made where the element being inserted belongs. In other words, before you insert an element, you need to find out where it belongs based on the BST rules. After insertion, you then need to ensure that the tree is still balanced or AVL compliant. What that means is the balance vector must not be more than 1 and must not be less than -1. If it happens that the balance vector does not fit within that range, you need to balance the tree. Now, with a deletion, deleting any node will at the end require you to again calculate the balance vector to determine if the tree is still balanced over the deletion. If it is no longer balanced, you need to balance it again. Now, this principle I've spoken to or about before. That is, when deleting a node that has children, you have to replace that node with the highest or largest child of the left subtree or the smallest child of the right subtree. Okay? The next one is find, which is basically used to locate a node with a particular element in a tree. Alright, let's now delve into some examples. Given 18, now, the tree originally ended here. When we check 18 is greater than 10, it's greater than 15, but when we compare it with 20, it's less than 20, therefore 18 will sit there. Alright, perfect. So after inserting, we have to do something. We have to determine the height of the tree. To determine the height, this is height 1, 2, 3, 4. This is 1, that is 1, okay? Because they've got no children. Perfect. Now that we've got the height, what we need to do is to calculate the balance vector. And let me show you how we do that. For 18, the balance factor is 0 minus 0 because it has no children. And therefore, for 18, the balance factor is 0. For 20, the balance factor is 1 minus 0. Okay? Because of this 1 and the 0 of the fact that there's no child, therefore the balance factor becomes 1. For 15, the balance factor is 1 minus 2. Okay, so it becomes minus 2, rather minus 1. So it is still within that range. For 10, though, the balance factor is 1 minus 3. 1 minus 3 gives us minus 2. That is outside the range. So there's a problem somewhere. Let's check where the problem occurs. The problem occurs here in this areas marked red. Oh, but we can see that this looks familiar. It looks like a right rotation is required here. Okay? So what will happen is we have to do that rotation that you have seen before. And after you do the rotation, 15 becomes the root. All that does is 10 comes down and becomes the left child of 15. And because 12 is bigger than 10, it will become the right child of 10. And 5, the left child of 10, which is what you find here. This is all that happened. When 15 became the root, 10 became its left child, and the child which was the left child of 15 became the right child of 10 because it is bigger than 12, bigger than 10. And as simple as that. Now, let's insert 19 and see what happens. When you try to insert 19 here, you'll notice that 19, when you look here, it's bigger than 19, it's less than 20, therefore it can't be here, but it's greater than 18, therefore it will be like that, which is why you have it here as the right child of 18. You now remember how this angle looks like. That we have come across before, and therefore it will require 2 rotations. But before we get ahead of ourselves, let's do the calculation. We determine the height 1, 2, 3, 4, and then we assign the values to the rest. And I'll just start there. I'll not determine for 19 because you know it's 0 because it's 0 minus 0, and then for 18 is 0 minus 1, so it's minus 1, so it's still fine. For 20, it's 2 minus 0. That's a problem because 2 minus 0 gives us 2. Therefore, we'll need to address that. In addressing that, we will need to rotate 18 and 19. 19 will then take this position, but because 18 is less than 19, it will be the left child of 19, which is why we end up with a left skewed sub 3. We know we have come across a left skewed sub 3 before and we know how to deal with it. If you go and calculate the balance factor, you'll still notice that it's still 2. It's still 2, as we had done before, because nothing really much has changed here. It's still, when you look here, just to show you, it's still 2 minus 0, because there's no right child of 20, and it gives us, therefore, 2. Okay, moving from that, we'll then now move on to do the rotation that takes 19 up. Therefore, 19 here will then have 18 as its child and 20 as the right child, and your 3 is now balanced. Should you struggle to understand how all of that happened, there are notes here on this block. Moving on, we want to now explore deletion and how that works. We want to delete 8 from this 3. Fortunately, 8 is at the very end, meaning it's a leaf node. After deleting 8, fortunately again, the 3 still remains balanced, and you can go and do the calculations. Remember, you have to assign the height. Here to be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Therefore, that is indeed 4. So it's as simple as that. You'll then do the balance vectors, which I've shown you how to do it. But suffice it to say that this 3 now shows 4 deleted, and this 3 still balanced. We will now want to remove 7, and that is 7. When we remove 7, all that will happen now, because 7 as a child, that rule kicks in. The largest the largest node from the left subtree, or the smallest node from the right subtree. There's nothing on the right side. There's only one child on the left, and therefore that will become the one that becomes A, and therefore it will take that position of 7. Therefore 4 will just go up, and there it is. When you do the balance vector calculation, you'll notice that it's still balanced, and therefore I won't even waste time in trying to calculate that for you. Okay, now we want to delete 11. Okay, trying to delete 11, the same rule kicks in. We have to replace it with replace 11 either with the smallest child of the largest child of the left subtree, or the smallest child of the right subtree. In this particular case, let's just change things a bit. We've been using the leftmost for the most part. Let's just use the right side of things, and we know the smaller one will be 12. Okay, on the right subtree. Therefore, we replace that with 12. And it looks good, 12, and then you have that as the reconfigured subtree. That 4 is still there, and then that 13 becomes under 12, and that's it, and everything still looks fine. The 3 still looks balanced. There's no need to reconfigure anything here up to so far. Okay, and you can go and do the checking of making sure that you assign the relevant heights as well as the associated balance vectors. All right, when you're doing this with your pen and pencil, I would advise that you use perhaps different colorings for the height and then for the balance vector. For instance, you could use a pen for the height and then a pencil for the balance vector, so that you are able to know which value represents what. Okay, now we want to delete 14, which is at the top. Remember the principle: the biggest child on the left subtree, which is 13 here, or the smallest child on the right, which is 16 here. So we can either replace it with 16 or 13 really, but for this particular case we'll just replace it with 13. Therefore 13 went up, and then we had that, and the 3 is still balanced, and you can check it out to verify that it's still balanced. Okay, so we're happy. Just remember, with every deletion you still need to check, is the 3 still balanced? How do you know if it's balanced? You do the calculations. Okay, now let's look at the complexity. Insert, remove, and find are all of order log n complexity, which looks good. It is quite a drastic improvement from what these were with some of the older methods that we have learned, which was of order n. Your top, size, and so forth are still of order 1, which is fine. It has been like that for a while. Okay, in conclusion, AVL trees are basically high balanced binary search trees, whose balance vector should be between -1 and 1. We've also introduced in this lecture the operations for insert and deletions through examples to demonstrate how those work. And lastly, you were introduced to the left-left, left-right, right-left, and right-right rotations. Simply put, the zig-zag or single rotations and the zigzag double rotations. With that, we conclude this lecture, and I'd like to ask you to pause this video now and do this exercise before viewing the solution. Remember, trying to cheat and going straight to the solution will be counterintuitive, because you will never really know if you will be able to do the problem. So please pause the video now and focus on solving the problems, and move on to the solution to compare with whatever it is you have come up with. That is the solution. I won't even discuss it. After all of this, one could only do so much in a short video like this one. To supplement the learnings from this video, please go and visit this material, which will assist you with all the material that I've just shared with you, but further with the associated code for the different stages and the different operations. I want to thank you, and I wish you the best.